So thank you. Thank you everybody for joining us. We're happy to have with us today Greinecker. He's from NS Paris-Saclay. He has varying range of topics that he researches, from measure theory to uncertainty, matching, core. And today he's going to talk to us about sequential equilibria in a class of infinite extensive form games. Michael, the stage is yours.
Thank you. So this is joint work with Meier and Konrad Podczeck, and we are trying to make the refinement literature a bit closer to what sometimes demanded in applications. So, well, everybody here knows sometimes Nash equilibria are not behaved the way you think should be a self-sufficing solution concept. So there has been a small literature on equilibrium refinements. So this is a special selections. More did not fit on the page. And this was a very extensive project, but it was almost exclusively focused with a lot of intellectual energy on finite games. Now, much of what we do when we do more applied economics, starting with Konrad and Bertrand, really has things like continuously varying prices, quantities, location choices, which makes everything kind of outside of the scope of this whole refinement literature. There's a relatively small literature on refinement for infinite games that focuses on simultaneous move games or normal form games, which in this situation usually don't represent any kind of non-trivial extensive form games. I think there are two papers on Bayesian games and refinements. So Janos is one of the co-authors there, but it gets relatively small when one looks at more non-trivial extensive form structures. And there are pretty good reasons for this. So one point I want to make is general infinite extensive form games are very badly behaved objects. So the usual assumptions that we impose, say, in simultaneous move games, the kind of continuity and compactness assumptions we impose, do not really give rise to a nice structure because they're implicit further discontinuities. Such games often suffer from so-called informational discontinuities. And one of the claims we make in this paper is that essentially all the problems and weird things that can happen in such games come from such informational discontinuities. And we restrict ourselves to games in which we assume these informational discontinuities away. And once we've done this, in games where information behaves nicely continuously, we can get a fairly natural definition and existence notion of sequential equilibrium. Now, sequential equilibrium, we actually have to kind of redefine. It's not just that we have additional assumptions that make it exist, because the classical 1982 Krebs-Wilson definition of a sequential equilibrium makes it inherently not directly applicable to the kind of games we're looking at. So we're looking at games that are like in discrete time and where players might have a continuum of actions available. Now, of course, sequential equilibria are defined in terms of consistency, which is defined in terms of completely mixed strategies that put strictly positive I mean here, strictly positive probability on all available actions whenever at each information set, and with an uncountable set of actions that is simply not possible. You cannot put positive probability on uncountably disjoint events.
Could I ask one question?
Sure.
So what about, say, the infinite of repeated offers bargaining game by Rubinstein, which is perfect information?
Yes.
There you can look at a subgame perfect equilibrium, which would be sequential. I mean, how does that fall outside your scope? I mean, it's both continuous and even infinitely repeated. I mean, in the sense that you can split the offer in arbitrary ways. So I wonder where to place that in your context.
Well, it is not within the class of games you're looking at. It is, of course, subgame perfection has been applied. What I mean is there's not much work on the structure of equilibrium refinements in finite games. Of course, there are lots of papers on subgame perfect equilibria in some class of infinite games. So I'm not saying nobody ever applied any refinement to any infinite game.
Okay,
They're also like
you will
specialized.
define, yeah, okay.
I will give you
define
the
what
class of games I'm looking
yeah,
at, yes.
yeah.
Michael,
Yes.
can't you restrict yourself to continuous distribution, mixed action with density, and then require that the density is strictly positive?
I think we do something in that kind of direction later, which imposes some kind of conditions of what we can do. Now, but the one very simple take-home lesson from this slide is just applying the definition of a sequential equilibrium as you find it in textbooks does not work. One has to find some reformulation that is ideally as close to the spirit of sequential equilibrium as possible. And luckily, we are not the first person to think about this. So Roger Meier and Phil Rainey have extensively worked on this question, and they have found some characterization of the kind of strategy profiles associated with the sequential equilibrium. And we also use this as our starting point. So we start with a certain characterization of the kind of equilibrium, the strategy profiles in a sequential equilibrium. So infinite action spaces are messy, infinite conditional beliefs are even messier, so we are trying to keep them out. So it is about standard finite extensive-form games. What does that mean? Finite extensive-form games of perfect recall, in which whenever nature moves, nature plays everything with strictly positive probability. And in these games, the following are equivalent. First, a strategy profile is part of a sequential equilibrium. And secondly, it is the limit as epsilon goes to 0 of a sequence of completely mixed strategy profiles that are conditionally epsilon best responses to each other. So at each information set, everybody has a conditional epsilon best response to what everybody else is doing, not just ex ante, but conditional. Of course, this is still not the solution for the problem because it still uses completely mixed strategies. And the approach of Meier and Rainey is to really try to get something as close to completely mixed strategy profiles as possible for the setting. So, well, what is their kind of substitute for sequence of complete mixed strategy profiles? Well, they take generalized sequences, nets, with the property of strategy profiles, with the property that eventually every action has strictly positive probability and some additional conditions. Now with nets that's possible, they have larger index sets, need not be linearly ordered, and this is something that actually makes it possible to make everything eventually have positive probability, though not at the same time. Now, what they then do is they show that they prove the existence in a class of games of conditionally epsilon optimal strategy profiles to each other that you can find as limits of such sets. So if you go to the characterization results, the next step is taking epsilon to 0 and taking a convergent subsequence. Now, generally, that's not possible. They impose a very fine topology on the strategy spaces, so there are no convergent subsequence, and there's no limit strategy as epsilon goes to 0. Still, maybe you don't care about strategies, you care about the actual behavior of what happens along a play. So you can look at the distribution over plays that is induced, and they take limits there. So they take the limits, measurable set by measurable set, and there exists some subnet. It's a non-sequential limit. The space is compact or not sequentially compact as outcomes that go as epsilon goes to 0. And that's then the kind of solution distributions they're looking at. Now, these limit distributions may not be induced by any actual strategies. These are, and I will give you an example of something like this happening later. A very simple example. There might not be any strategy that actually induces the limit distribution. And this limit distribution, in the kind of topology they use, need not be countably additive. This need be finitely additive measures that fail to be countably additive. This might look like a purely technical issue, but finitely additive measures on a sigma algebra that are not countably additive are extremely non-constructive objects. You need fairly heavy uses of the axiom of choice to show they exist, and they are not something you can actually write down. So if you want to solve a game in an applied project, and then you want to write down the solution, there's no real natural way to define finitely additive probabilities. Of course, things like CDFs that work in the countably additive settings are not available. Now, these kind of problems are not problems that come from them not finding a sufficiently clever way to do things. These are really problems that are unavoidable. They have plenty of examples that in some sense one cannot do better in the kind of class of games they're looking at. So what we want to do is we're looking at a class of games that's a bit nicer behaved and get much stronger results. And conceptually, we also want to de-emphasize the role of completely mixed strategies, because in the sequential equilibrium, they play less of a role as it might seem. So what they really do is they guarantee that all information sets are reached with positive probability. So every kind of situation a player can ever find themselves in occurs actually, but it does not have any additional role as say in perfect equilibrium, where it provides us a certain kind of local admissibility condition. So we rewrite the characterization result of Meier and Rainey, same condition, finite extensiform games, an equivalence result for strategy profiles. So it's equivalent to have a strategy profile as part of a sequential equilibrium, or it is the limit as epsilon goes to 0 of a strategy of profiles in which each information set is reached with positive probability, and that are conditional epsilon bus responses and so on as before. So we weakened the condition of completely mixed strategy profiles, which would kind of ensure that every node in every information set gets reached with positive probability, to a condition that says that in each information set, one node is reached with positive probability. Now, this is still not a completely satisfactory solution. If players move more than once, information sets contain information about the past actions of a player, and if there's a continuum of actions, you cannot put strictly positive probability on a continuum of information sets. Still, the spirit is that there are certain events, here the information sets, where you want to test optimality or epsilon optimality. And I want to convince you later that there's a slightly smaller class that still does this job. So that's kind of our approach. So what are the kind of games we're looking at? We're looking at multi-stage games. So time is discrete, and they are like this. They are like periods. The time horizon is infinite. Of course, you can restrict yourselves to finite games. In the first period, period 0, nature is active, and nature is only active in period 0. Then nature makes a choice, but for a technical hack we want to apply, we call it an observation nature makes. So nature observes a signal from a signal space given a certain distribution. And then in the next period, there's one active player and 1. So in each period, there's exactly one active player. That player observes a signal of their own, whose distribution might depend on everything that happened before, in particular here on the signal nature observed. And then that player chooses some action. For the purpose of this talk, the action spaces do not depend on histories. In the paper, they do. And then in the second period, in period 2, there's again an active player, could in principle be the same, observes a signal. Now, importantly, the signals are kind of the additional information a player gets. They're not the same thing as information sets. We implicitly force later perfect recall by letting players allow the behavior to condition on past private histories, but this is kind of the signals are kind of the new information that arrives. And here for Blair in period 2, this can depend on all signals from before and all actions before, and the player chooses and so on. So this is kind of, if you want to have simultaneous moves, we can as usually make it that one player does not observe what another did, and then they're kind of logically moving simultaneously. And if we also include, as we do in the paper, history-dependent strategies, the main thing we're excluding are weirdly crossing information sets, situations where players don't know where in time they're relative to each other. Now we impose some assumptions. So that we impose first the kind of assumptions that you think are the obvious assumptions. So, well, each signal space is separable, completely metrizable, say the real line. Each AT is compact metrizable, say the unit interval, and we put enough structure in our signal spaces that all probabilities are well defined. Now, for a game, there's still the payoff function missing. So each player has a bounded payoff function that should be measurable in signals. So signals can be payoff relevant here, and it should be continuous in everybody's actions. And this structure is kind of not enough. So even if you would say, make signal spaces compact and signal functions to be continuous in the topology of weak convergence, this is not enough structure to get any meaningful theory going, because there's still possibility of implicit informational discontinuities. And our claim is this kind of informational discontinuities are going what's driving all problems that you find in this literature. And I will give you an example. It's a very, very simple example. It's basically a very slight variation on matching pennies. So there are two players, Anne and Bob, and you play for 2 rounds. In the first round, Anne chooses a number between 0 and 1, and Bob chooses the number 0, 1. And then in the next round, Anne observes the product of the 2 numbers, and she chooses 0, 1 herself. So the 0, 1, these are the kind of matching pennies parts. And payoffs are that Anne wants to match Bob's action. So the closer she is to Bob's action, the better it is. But there's also a cost Anne has to pay from her action in the first period. And Bob wants that Anne mismatches his action as much as possible. Now, very naively, action spaces are compact, payoff functions are continuous, the product of 2 numbers is continuous, and if you want to be more fancy, you see this as a function on probability distributions over signals, it is continuous if you impose the topology of weak convergence on those signals. However, this game has no Nash equilibrium, and that's not terribly hard to see. Well, suppose there would be an equilibrium. Either N would choose, or at least with positive probability, a positive number in the first round. Well, then in the next round, she sees the product of the 2 numbers, can divide by her number, and she knows perfectly what Bob does. Then, of course, she wants to match exactly what Bob does. It means the matching pennies part of her payoff is going to be 0, as high as possible, but she still pays the cost for the first period action, and she could have done the same thing with a slightly smaller action. So it can never be optimal to pay a positive number. But if she plays 0, then in the next period she doesn't learn anything, and then Bob can randomize 50-50 in the first period, and they're basically matching pennies. Her expected payoff is going to be 1/2, and she could do better by choosing a small a1 smaller than 1/2. So this game doesn't even have a Nash equilibrium. There's nothing to refine in this game. And even though things look from, if you don't think too deeply about it, very continuous, they're really not, because what Anne learns from her signal varies very discontinuously. If she plays 0 in the first period, she learns nothing. If she plays any ever so small positive number, she learns everything. So there's an informational discontinuity that drives this non-existence here. And this example also illustrates another phenomenon, namely that if you just look at the kind of distributions over plays that are induced by some strategies. In this game, this space is not going to be closed. You can see this the following way. Take some sequence of positive number n placed in the first period that goes to 0. Then along the sequence, she observes exactly what Bob does. Bob randomizes 50-50 and n matches Bob perfectly. Along the sequence, the matching parts, they are perfectly correlated 50-50. So they must also be perfectly correlated 50-50 in the limit where n plays 0. But if n plays 0 in the first period, she doesn't have the necessary information that she would need to perfectly correlate with Bob's behavior. So here the space of distributions is not closed. That's something Meier and Rainey call strategic entanglement, because there's some kind of correlation device that disappears in the limit. And this makes these kind of games also a bit technically badly behaved. And one of these first papers that observed that this problem can occur is a 1985 paper by Milgrom and Weber, and introduced some assumptions. So there was a paper about existence in Bayesian games. And this introduced some assumptions that we modify in a dynamic way. That's our main assumption. This is just said, sorry. So we have a continuity function, a very strong one, on signal function, and it goes like this. For every period, there's some probability distribution on signals, and we have some function that depends on histories, stuff that happened before period t, and the current signal, so that for every history, the corresponding section is a density with respect to mu t of the signal distribution, a rather Nikodym derivative. So that's what Alon suggested. Information here comes with densities, and this, for example, excludes the kind of information assumptions we have before. If you learn something another player did perfectly, you need to have a mass point. That means you can only learn countably many things other people do perfectly. And otherwise, you force some kind of noise in the process. We assume the densities, parametric densities, are continuous in action, and they satisfy an integrable boundedness condition. And as I said, this is kind of adapted for Milgrom and Weber, using some improvements from paper by Balder, and most closely related, there's a working paper by Sofia Moroni. The newest version is from summer, June this year. And what she does is she looks at dynamic games where you have a continuum of signals and types, but only finitely many actions available. And she has an assumption like this that she uses to show that perfect and sequential equilibria suitably defined exist. But she looks at a class of games in which completely mixed strategies exist. But yeah, so that's the paper, and it's very much worth reading. So this is the continuity assumption we're going to impose. It's not naturally satisfied in many economic models, but it's also in some sense, in many cases, something that's not too unplausible. You observe a quantity another player played, how much the farmer next to you planted. Do you know it exactly, every single little grain? If not, maybe there's ever so slight kind of noise that you can give it by density, and then you're in a class of game we're looking at. Now, part of the categorization results has something to do with convergent sequences of strategies. And strategies are complicated, measurable functions, so we want to make life a bit easier by dropping some information. So here's because strategies contain a lot of additional information. So suppose you have an undergraduate game theory course, and there's the assignment for this little game to find a Nash equilibrium which is not subgame perfect. And the student comes with a solution that n plays left here and Bob plays left here, and that's the solution. And then the student doesn't get all the points for his assignment, complains to the instructor, and the instructor tells him, well, n playing left is not a strategy. A strategy doesn't just have to specify n playing left, it also has to specify what n does in a second decision node. And then the student says, but if n plays left, well, why Is it relevant what n does in the second node? She's never going to play here. And then the instructor says, well, that's the official definition, and there's nothing we can do. But of course, if n plays left, what she does in the second node is irrelevant. And this is something that Harold Kuhn observed in what was maybe the first game theory course ever in 1952. The lecture notes have been published a bit later. And Rubinstein kind of discussed it. Maybe strategies include something like beliefs other players have in some sense, and they contain a bit more than just a plan of actions of what they're going to do. Now we are following Kuhn, Rubinstein, and our undergraduate student, and are happy to ignore what n would do in the second node if her behavior forces her not ever to go there. Now, how do we implement this now? In terms of something called strategic measures that we adapted from the dynamic programming literature. So the strategy plainly defined, it takes the private histories, the stuff that the player knows, and maps it to probability distributions over actions. So these are kind of behavior strategies. And we look at an induced object that goes the following. You look at the first time some player observes the signal space in some period t, we choose the signal with respect to this underlying probability distribution, and then apply what the player does there and get a joint distribution on these signals and actions. Then independently, the next time the player observes something, we select the corresponding signal, and now we have a distribution over 3 objects, apply the strategy of the player, and get a distribution over signals and action 2 periods, and we can continue so to get a whole distribution over all signals and actions of a player. Now, and we call the kind of images in these distributions strategic measures. If every player plays just once, this is exactly the same thing as the kind of distributional strategies of Milgrom and Weber. And mathematically, these have been discussed in detail in the literature on non-stationary stochastic programming. So especially since a paper by Manfred Schill in 1975, where the idea that maybe we should look at conditions that say the space of strategic measures is compact, the distributions actually induced by strategies, policies in their lingo, and so that, say, the target functions upper semi-continuous, then we know optimal solutions exist. And we can kind of piggyback on this whole literature. And of course, the very definition of these strategic measures is based on our idea that we have these underlying probability distributions. Formally, they depend on the specific underlying probability distributions, but this is a problem that has a solution that I don't want to go into right now. Now, these are very well-behaved objects. So first, conceptually, if 2 strategies induce the same strategic measure of a player, then irrespective of the strategies others are doing, you get the same distribution over outcomes. That means you can do most reasonable analysis in terms of strategic measures. You also have a very nice mathematical structure. So in the weak topology, they are compact. That's in this setting where action spaces do not depend on histories, basically from a result by Novak. Otherwise, a little bit of work is needed. And they can be linearly embedded as a compact, convex, traceable set in some suitably topological vector space, and in a way that expected payoffs are continuous and multilinear. If any of this looks strange, what this basically says is there's enough structure that we can do the standard proof that Nash equilibria exist. You can just apply the Kakudani-Van-Klicksberg's theorem, and there must be at least one Nash equilibrium in distributional and strategic measures, which all correspond to real strategies. So the problem that there's no Nash equilibrium to begin with does not occur. We have something that we can refine, which is what we want them to continue with. So there's some Nash equilibria, and there's a nice structure. we have a natural notion of convergence for these objects. And the kind of information strategic measures loses is exactly the kind of stuff that our undergraduate students ignores. So maybe I should have mentioned this before. So suppose you have something that you choose in every period the same action, irrespective of the signals you have observed before. This gives you a well-defined strategic measure, unique path kind of from this distribution, but it doesn't give you a strategy, because a strategy will not just tell you, you do this in the first period, this in the second period, ignoring all other information. It will also tell you, you do this in the first period, this in the second period. And if you would have done something in the first period, which you did not, you would do something. So this is the kind of information we ignore and that we are kind of happy to ignore here. Now, so far, this is mostly showing that the games we look at behave like simultaneous move games. And actually, these kind of strategic measures, you can think they're closer to mixed strategies than they really are to behavior strategies, which later will require a bit of playing around in the proof. But let's go to the crux of what happens in extensive form games. So there's this typical truism that in extensive form games, you cannot ignore probability zero events, and the usual laws of probability don't work anymore. So for example, to take the equilibrium, let's follow a student in which n plays left and Bob plays left. Well, it's an equilibrium because Bob optimally responds to n, because the event that Bob actually has to make a choice has probability zero. If Bob would actually choose, Bob would of course play right, which gives him a payoff of 1 for sure instead of 0. But of course, Anne, when she makes her choice in the beginning to go left or right, she has to think what happens if she goes left, what happens if she goes right. And the only reason that Bob's choice does not matter is because Anne does make it so. So a kind of converse to the idea that probability zero events can matter is that other players can make sure that they do occur as positive probability, is that things that can never occur as positive probability, irrespective of what everybody is doing, should not matter. So we want to ignore things that happen with probability zero, irrespective of what every player is doing. And this puts some restrictions on what we can do. Now, information sets, our characterization result, was about strategies in which all information sets get strictly positive probability. And information sets here are basically combinations of signals, past signals, and actions. The signal part has a nice solution. You can construct, under our assumption, strategy profiles under which every set of signals that can have ever positive probability gets actually chosen simultaneously with positive probability. So if every player just moves once, we have a perfect analog to what we're doing here. But we don't want players to just move once. And if players also have to remember their action at some point, because they play twice, then we have the problem that information sets will contain past actions, and you cannot, since we cannot put positive probability on all actions, we cannot put positive probability on all information sets either. So it's not possible in general to have any strategy profile under which all information sets get positive probability. Now, why do we want to have information sets to have positive probability? Well, we use this as the points where we test rationality on its characterization, epsilon rationality. Are people really epsilon optimizing? So, and it turns out maybe we can allow a little bit of slack in that dimension. Maybe it's not necessary the players have to condition exactly at previous actions. Why is that the case? Well, our assumption guarantees that everything is continuous, distributions over plays, expected payoffs in particular, information structure, particular expected payoffs. If something is epsilon optimal at some information set with epsilon a strict inequality, then since payoffs are continuous, it would also be epsilon optimal for close by actions. That means when we look at testing for epsilon rationality, we can allow a bit of slacks in the kind of actions. We don't have to look at all possible histories of actions. We can have some kind of openness requirement, and this is going to help us deal with this problem here. So we use strategic measures that reach what we call observable events. They're a bit stronger than what Meier and Greinecker call observable events. And these are the things we want to condition on. These are the things where we want to test epsilon rationality on. So we look at a player I that is active at some period t, and a set F of finite sequences of past actions and signals up to now. So these are exactly the kind of things player I is going to condition on their behavior in period t. So these are kind of the relevant information sets in period t. And we call a set of these objects observable if, but first, it should be reached with positive probability under some strategy profile. If it can never be reached with positive probability, it is kind of strategically irrelevant. And the other condition is, that's the kind of slack condition actions. If certain sequences of signals and actions is in the set, then there must be a small open neighborhood of this sequence of action, so that everything if we change the actions to something in this neighborhood, it is still going in the set. So this is what allows us to introduce a little bit of slack, and it's actually possible to put positive probability on these objects. So we say a profile of strategic measures is informationally complete. This is kind of our analog to strategies in which all information sets are reached with positive probability in finite games. If every such observable set is reached with positive probability, and luckily this stuff actually exists. So there are informationally complete profiles of strategies, and this gives us one part of what we need for our characterization of sequential equilibria. Now, the next thing we want to do is, how do we do this whole conditional optimality? So we test sequential rationality on observable events.
May I ask one question?
Yeah, sure.
Can you come back to the previous slide? So why do you call this observable?
Well, the observable part is kind of the first thing. It's something that can ever happen with positive probability. And
how is condition 2 related to observability?
Well, the idea is, in some sense, it's something that's conceivably observable when players play the game. That's in that sense. It's something that you as an outside observer might see when players play the game, because it can happen with positive probability.
Okay, so condition 2 is not related to observability.
No,
it's condition 1.
If you short set it like I am and you don't see the actions too closely, then it's nice to have a neighborhood, but yes.
Okay.
Okay, so we want to test sequential rationality or sequential epsilon rationality in these events. Now, it's pretty clear what continuation strategies are, but here we work with strategic measures, so we have to find a kind of analog. And we say a T continuation of a strategic measures is a strategic measure that has the same marginal on things that happen with positive before T, and then you can do whatever it wants. So this represents a player who's forced to play a T continuation, means they have to play according to strategy before, and starting with period T, they can do whatever they want. In particular, these are the things where we want to say that starting with period T, we will look at where the behavior is optimal. And we say that a profile of strategic measures is conditionally epsilon optimal if every observable set that is actually reached in the strategy profile at some period T, that the player chooses a T continuation among all possible T continuation that is within epsilon of the conditional optimum. So this is just our notion of having epsilon conditional best responses. And they're here well defined. The one thing that's a bit subtle is that, in some sense, to make things fit together well, when we don't have strategies but strategic measures, we cannot change the probability with which an event is reached. But this makes things work. Okay, so now we have all the ingredients to combine them to get our definition of sequential equilibrium. So we say a sequential equilibrium is, and here we say it's actually a sequence, and I'll tell you in a moment why, of informationally complete profiles of strategic measures, such that for every epsilon, all but finitely many of those are conditionally epsilon optimal. So we require uniform optimality on all these observable events at the same time. And why do we have the sequence? Well, in the limit, there's information getting lost, especially since we have this kind of plan of action, strategic measures. We lose even more information in the limit. So what happens along the sequence is kind of a substitute for the beliefs. And if this would be a finite game, the sequence of beliefs, well, that are uniquely induced, any limit point of this is exactly what your system of conditional belief would be. Now, by construction, if we have a standard finite game, this is exactly the same thing as a sequential equilibrium. And since I made a big production of all these continuity and so on conditions, of course, a sequential equilibrium exists. Now, the proof is as close as possible to something like the proof that extensive form perfect equilibria exist. We want to construct some kind of perturbed strategy spaces, find Nash equilibria for those, and take limits as epsilon goes to 0. Now, the one thing that's a bit more complicated here that requires a trick is we're not working with something like the agent normal form and behavioral strategies. We get nicely the conditional structures. You're basically doing something in the space of mixed strategies. And they're making the conditioning go work requires a bit of work. And here's how we do it. So we construct some kind of ancillary games in which players are not completely free to choose what they do. So we fix some informationally complete profile of strategies, of strategic measures, and pair functions in our model are bounded. Let's assume they have values in 0, 1, because we construct things in a way that sometimes players are forced to do something that might be suboptimal. Otherwise, they can do what they want, and in equilibrium to play optimal. But then we know that if they play suboptimal in some equilibrium, it must be because they've been forced to do something stupid. And then the probability of playing something stupid is an upper bound for how much can go wrong in terms of their payers. So the way we construct strategy is kind of as convex combinations or like infinite convex combinations of different sets of strategic measures. And we can interpret them probabilistically. If you have two sets of strategic measures and you play this one with probability 1/2, this one with probability 1/2, so you take 1/2 this plus 1/2 this, you can think of a player who's forced to choose from the resulting set as someone whose probability 1/2 is forced to choose from one set, with probability 1/2 is forced to choose from the other set. And that's kind of the interpretation I'm going to use in what we're doing. So we fix some natural number that is less 2, and if some player is active at t, we make them choose with a probability of 1/mt a t continuation of beta I star. So they have to follow their strategy in this information complete profile up to everything before t with a probability of 1/mt, and then they can do whatever they want. And if m is strictly larger than 2, this will sum always to something smaller than 1. So with the remaining probability, they can do whatever they want to do. And then we're looking at Nash equilibria where strategy spaces are restricted this way. Now, one thing that's relatively easy to say is that if they're restricted this way, they have to play something informationally complete, because every event, that observable event, happens in some period, and the kind of parts of beta star that lead to these events will be played with positive probability. What's a bit more subtle is that we actually get the conditional epsilon optimality for all events. And the claim is, if we look at this restricted game, every player will play 1 over m conditionally optimal at each observable set. So how does this work? Well, they're in a Nash equilibrium, and with a certain probability, they are always free to do things, whatever they do, and then they will behave optimally. In particular, if they have no restrictions whatsoever, or they choose something that is a previous t continuation or a t continuation, an event in period t, that means they can from now on do whatever they want. They will necessarily play as best response. So the only suboptimal behavior in an event observable in period t comes if they're forced to choose a continuation of some later t. However, the probability that they do get to the event in period t, given they're forced to play a t continuation, is exactly, because before period t, they were forced to behave exactly according to this profile, is the same as if they would play some later continuation, which they do with much, much smaller probability. So if they do play in a restricted game, the probability that their behavior comes from the part where they're not restricted in period t is much, much larger than the conditional probability when they are restricted, and this gives that they are 1 over n conditionally optimal. And I understand that this is not so easy without pen and paper, but that's the basic logic, I think it's. And that's kind of what I wanted to tell you for now. So infinite extensive form games that satisfy the typical assumptions we have are not well-behaved objects. They are not very nicely because they suffer from informational discontinuities that we can, with one single assumption, assume away. And in the remaining games, we have a definition of sequential equilibrium that we think is somewhat faithful to the original 1982 notion of Krebs and Wilson. And that's what I wanted to tell you for today. Thank you.
Thank you. People, if you have any questions, please feel free to unmute yourself.
Yeah. May I ask a question? Thanks for the talk. In your example, like matching pennies with Anne and Bob, so there was no Nash equilibria, but
Yes.
there is a Nash equilibrium payoff. So for each epsilon, there is an epsilon Nash. And,
Yes.
And 0, 0 is like a limit of epsilon Nash equilibrium payoffs.
Yes.
For me, there are two things. I don't understand how related they are. One is the existence of a 0 Nash equilibrium, and the other one is a continuity of information. So do you think that there may be a theory where you could have a definition of sequential equilibrium and you will have existence that will coincide with the standard finite games, but which will not imply the existence of a 0 Nash equilibrium?
Well, yes, that exists. That's like what Meier and Rainey have. Meier and Rainey have exactly epsilon equilibria, and they do allow for certain games in which actually like also a 0 Nash equilibrium does not exist. So there's an example of a signaling game by Alejandro Manelli that has no Nash equilibrium, and this kind of signaling games, they're included in the class of games they allow for.
But
So
you can combine what they do and what you do?
No, so I think what they do is very strongly driven from the kind of Tychonov compactness, which makes compactness very simple, convergent nets and so on, but doesn't give us much structure and doesn't give us things like countable additivity. So I think it's there's sufficiently different approaches. It's not easy to find like something in between. At least I would not know how to do that.
Thank you.
Yeah.
Can I ask a question quickly?
Sure.
But I can still ask the question in your nice games, whether your notion and the notion that Meier and Rennie have, whether they agree in these nice games.
That's true. So the thing is, what they do really is to define epsilon equilibria and then they don't take limits. What can of course look is, you can ask whether Meier-Rennie epsilon equilibria in a section of our game converges to something like this. I think that might be true, though I'm not sure the intersection of our games is formally that large. But yes, I think that's definitely on the to-do list in how to look at how the two solution concepts compare when they have a shared domain. That's right, yes. But I don't have an answer for this.
Question. So
Yes.
I think you have not ruled out the possibility that some players have a finite set of actions, right?
Yes.
So, well, first of all, there are some very simple infinite games for which the sequential equilibrium Krebs-Wilson can be defined in a very, very simple way. And it is, games where, let me say, for example, games with a finite number of stages, where in all stages but the last one, players have a finite action spaces, and in the last one they have a compact set of actions, and payoffs are continuous in the obvious way.
Yes.
For those, this is a class of games I consider for different reasons, to extend notions of rationalizability for dynamic games to infinite games. Obviously, you can consider, also games with infinite horizons, as long as you don't have this problem that of observing something continuous, right?
Yes.
And related to this, you are assuming that the active player who plays may depend on calendar time only. Okay.
Yes.
And I think the reason is that if actions are continuous, making the active player depend on previous actions creates a discontinuity, basically, because there is a finite set of players. Maybe that was the reason.
So I do think sometimes you can get it around with hacks, like making a player say move twice and then making dependent which of these actions matter on some other player. It's mostly because, so we didn't try very hard to get rid of this assumption, because it allows in some sense an easy treatment where everything is a nice stochastic process that evolves over time in the usual way. And we would have probably to redo a lot of existing stuff. And I'm not sure that for most applications the cost is that high, but so there's no obvious technical restrictions that force us to do this. If you have something like, if a strategy space is say 0, 1, of course this space is connected, but then if you have, you can still do something like taking 2 disjoint copies of 0, 1 as a strategy space. So I don't think this connectedness is inherently a problem, though it might be subtle how to implement things. But how far exactly you can go in that direction, I don't know.
Okay.
Thank you. I think there's something in chat. Okay.
I don't see anything in the chat. Are there any further questions? Okay. Well, if not, then we thank you again.
Thank you.
And I will stop the recording, so if you want to be less formal.